Hi guys, it's nice to be back. I've had Parkinson's disease for a while, and I have been out of action. So hope we can connect in a way so that these Parkinson's symptoms, which are normally very dominant, we can put them aside for some time and concentrate on the quantum mechanics. Different eras are characterized by their icons. The 19th century was the age of the internal combustion engine, and that resulted in a lot of heavy machinery being manufactured and distributed. 20th century was the information age, the age of the computer, the Sun workstation, the IBM PCs, and all that. And most recently, the iPhones. It was the information age, no doubt about that. The prediction is the 21st century will be the quantum age, when the quantum algorithms and different quantum techniques were coming about, and they'll mark the beginning of another age, which will be the quantum age. This was predicted around the beginning of the century. Paul Davies is a noted science writer. Classical computation consists of merely fast ways of calculating Boolean functions. These are ways which are very efficient, and especially with some semiconductor devices providing the added boost, the computers of today are very, very efficient. But then the question arises, two questions arise. One, can this trend be continued indefinitely? And second, how long can it be sustained? The answer comes about by looking at what the limitations of the present day transistors are. The transistors of today are approaching the point where we have to take quantum effects into account. What are these quantum effects? One looks at large macroscopic size systems, say, let's look at 10 to the power of 23 electrons or 10 to the power of 23 particles, and then do a computation with these. Computation means calculating of a Boolean function. One can do it with surprisingly fine accuracy. But then let us go to 10 to the power of 22, make the system 10 times smaller. And again, one finds one can do it with the same accuracy. 10 to the power of 21, 20, 10 to the power of 15, 10 to the power of 10. Okay, now 10 to the power of 10, some effects start to come about, and we wonder what's going to happen in the future. But no problems. Engineers are very good at redesigning systems. So you redesign around these effects so that these effects are noise. So you get down to 10 to the power of 5. Now these effects are very, very dominant. One is the system power dissipation problem, and second is the tunneling problem. Both of these become very significant, and engineers have a hard time redesigning them. So will the devices still work? Richard Feynman gave a talk in Bell Labs in 1985, which I had the privilege of attending. So an analogy he gave was that in the 1930s, when airplanes were just starting to be developed, then the question arose that whether they would be able to fly faster than the speed of sound. There were papers written that indicated that speed of sound was a fundamental limit for these kinds of airplanes, for most kinds of airplanes. But by the 40s, there were a series of developments, and just by clever design, they were able to redesign the airplanes so that they still worked. Supersonic regimes, they can still be redesigned, but the principles of design in the new regime were very different. Similarly, the answer was whether the devices will still work when the size becomes small. The answer is yes, they will, but the principles of design in the new regime will be very different. So we'll talk about some of these principles of design in this talk. That is the aim of the talk. That is as far as the limits of computation go. But can quantum computers do more than classical computers? Classical computers were mostly about calculating Boolean functions and calculating them faster and faster. Quantum computers can work around that. The power dissipation problem is addressed by reversible computing. The idea is that Feynman and others have proved that any function can be calculated in a reversible way. Any Boolean function can be calculated in a reversible way. It might take a lot of queries, but it will take roughly the same amount of queries that you would expect using an AND or NOT gate. And the gate leakage problem is also solved by having different kind of designs. The architecture, if you look at the architecture of any of those chips which have been redesigned, you'll find that they are wave propagations kind of things. Quantum mechanics systems tend to be more oscillatory generally. They may not be, but most of them tend to be more oscillatory in classical systems. But the question behind quantum computation is, once that question is answered, then one can relax a little bit and move on to other things. But the question was, the dominant question was, but can quantum computers do more than classical computers? This question was not convincingly answered before 1994. David Deutsch had a 1-bit system, but that did not convince as many people as Peter Shor's factoring algorithm did. Factoring is a problem that people have been working on for quite a while. Mathematicians have worked on it for quite a while, and they had pretty much given up on that. And Peter Shor came up with a very smart algorithm for that. That is polynomial time. The question was, classically, it had not been proven to be difficult, although it is believed to be difficult and someone has found an algorithm for it so far. So much so that security of RSA code is based on the fact that the factoring is a difficult problem. I mean, if someone were to find an algorithm for factoring, then all the transmissions, bank transmissions of the last 50 years are going to become public information. So what is this problem of factoring? If someone gives you 2 3-digit numbers to multiply, it is easy to multiply them fast. I mean, if you're given a piece of paper and a pencil, you could do it in 20 seconds. But given one large number, say 31977, which is the product of these two, and someone asks you to find what the factors of this number is, now there are no shortcuts. You have to look at all numbers up till square root of that number, which is roughly square root of 31977 is probably around 200. 200. So looking up to all factors up till 200, all numbers up till 200 to see if it can be broken up into those numbers. It will take you half an hour. Except if you have a quantum computer that knows Peter Shor's algorithm well, then you can do it much faster. The idea is that you're given a dictionary with 1 million words in it, and you have a crossword puzzle challenge. The third letter is R, the fifth letter is N, the sixth is H, and it's a 7-letter word. Find out what this word is. The classical system, if you were looking at it on a classical computer, if this dictionary was on a computer and you had to write a program to find out what the word is, you'd have to look at about half of those words on an average. I mean, that's because the dictionary is not sorted by the third, sixth, and seventh letter, third, fifth, and sixth letters of the alphabet. So you would be very hard pressed to write a program that took less than 500,000 words on an average. Quantum mechanical systems can be in a superposition of states, and they can be looking at different states simultaneously. So there is no clear bound as to what, how much a quantum program would take. Just to give you a heads up, quantum search algorithm will be able to do exhaustive search in just about square root of n steps, which is about, in our case, square root of 1,000 is square root of 1,000,000 is 1,000. So in about 1,000 steps, you'll be able to do it, which is taking you 500,000 steps classically. So before proceeding on to designing the quantum mechanical system, let us look at what a quantum computer looks like. The answer is it looks just like a probabilistic system. Instead of bits, we have qubits. Bit can be in one state at a time, while qubits can be in multiple states at the same time. A classical system is characterized by its probability vectors, probability in each state. If you can specify the probability in each state, you have the whole system specified. And you can do whatever calculations one can do with a classical computer. The difference is, with a quantum computer, it is very similar. The system is characterized by its state vectors. And a state vector gives, instead of a probability in each state, it gives something called an amplitude in each state. The difference is the classical operations take place directly on the probability vector, so that the probability vector is what gets transformed as a result of these quantum classical systems. And the thing that gets transformed in the quantum case is the amplitude vector. Classically, the processes that are of interest are Markov processes. And quantum mechanically, the processes, Markov means each column in the transformation should add up to 1. Whereas quantum mechanically, each column in that state vector should add up to, we don't know how much it should add up to. Turns out that there have to be unitary matrices, the transformations. The square of each column should add up to 1. That is because the probability is the square of the amplitudes that is conserved. In fact, this is a quote from someone I know. Quantum mechanics is simpler than classical mechanics if you leave out the physics. If you leave out all the weird consequences of quantum mechanics, In classical mechanics, it's simpler than classical mechanics. With classical mechanics, you need to worry about whether the system is behaving like a wave or a particle. While over here, it is the same rules for both waves and particles. The propagation will be like waves and detection will be like particle. So the architecture of a quantum computer will look very much like a probabilistic computer. Rather, the description of it in terms of matrices and vectors. Oh, one more thing. The amplitude vector, since they describe the amplitude of a system consists of the magnitude and the phase. So all these numbers in the transformation matrices will be complex numbers in general. They can be real too, but in general, they'll be complex. And the reason people find classical quantum mechanics so complicated is that it's usually associated with differential equations and Schrödinger's equation, solving Schrödinger's equation for a harmonic oscillator is a very tough job because you have the differential equations to solve. So I would suggest anyone who is trying to learn quantum mechanics, learn it with these quantum computation people rather than the differential equation people. So these are some of the transformations that we'll use later on. But let me introduce what they look like right now. Selective inversion of certain states. We assume that we can invert the amplitude in certain states. If we can calculate the function, Boolean function for a certain input, we can also invert the amplitude in a particular state. And notice this is unitary. All the columns are orthogonal, and all the columns, the square of the magnitude of each column adds up to 1. So this is a function that will be, and we can show how to implement it in a few minutes. So what this is a diagonal matrix. We are given a function. This is a block to calculate this function, which is 1 at one point and 0 at all the other points. And this is a matrix transformation that we can design that inverts the amplitude only in the state in which it is -1 and leaves the amplitude in the other states unchanged. Okay, the circuit which it inverts the amplitude in the state, I have already found one mistake. It should be 0 -1, not a 0/1. So it has an equal superposition, equal amplitude in the 0 state and the 1 state. The sign of the amplitude in the 1 state. So this fx x bar comes from here, and x bar leaves from here. And the other input is connected to 0 -1. Actually, I might have a better diagram of this later. So let me come back to this later. To summarize, this is what we have a quantum system looks like. We put the system in a superposition of the n states, and then if we were to do an immediate measurement, the chances of getting the desired probability is just 1 by n because it's just one of n states. Instead, what we do in a quantum search algorithm is amplify the amplitude in the state so that there's a higher probability of getting this particular state. And amplifying the probability turns out to be much easier task than repeated measurements of the same state. I'd say a much more efficient way. Repeated measurements of the state are easier to do, but it'll take you in measurements to get the right answer because the n states and none of them has any more chance of getting the right answer than the others. After this, if you measure the probability, there is a higher probability of observing the right state. And one can boost this probability in just about square root of n steps. I haven't found any simple explanation for why it should be square root of n or not up below that or above that. But people have proved that this is the most efficient algorithm there is, and it cannot be improved even by single query. This was actually before talking about the algorithm, let me first describe how the algorithm works. Okay, inversions, just inversion of the states, absolute in the states, is a unitary operation. We know that, and we presumably know how to do that. Just connect it to an inverter and take the output. Inverters are unitary operators, so they can be designed quantum mechanically. One transformation that is not known very well is the Householder transformation. Turns out people in linear algebra know it is taught in linear algebra, but it's not taught in elementary courses. It's a very useful way of inverting matrices. It has the same complexity of Gaussian elimination, but for some reason, Gaussian elimination is taught all the time, but not Householder transformations. Anyway, using Householder transformations are reflections around different axes. One place where Householder transformations do show up is in the interior point methods. It's a technique for calculating inverses of matrices. I should say it's one of the results of the techniques is an efficient way of calculating the inverse of matrices. The place this shows up is in interior point methods, where they need to update make small changes to the position of the interior point, and then update the matrices of the, what do they call it, that potential function. So using small changes, the matrices will only get updated by small amounts. And the way to do that is using Lanczos method, I believe. That's what it's called. The place it shows up is if you look at the complexity of calculating the extreme point in any direction, linear programming. To calculate the matrices, you need to calculate them square root of n times. The number of steps the interior point makes is square root of n. So if you were to use the standard method of calculating matrices, it would yield you about n to the 3.5, n cubed for each step, and square root of n steps, n to the power 3.5. While if you were to do it using Lanczos method, you could do it in n to the 3, I believe. It might be off by a factor of square root of n, but I believe you get a square root of n advantage by using the Lanczos method. The way we will use it is in our inversion about average. Using this Householder transformation, you can even show that the inversion about average is unitary. And it's inversion about average is a transformation that is synthesized by Walsh-Hadamard, selective inversion of 0 bar, and Walsh-Hadamard. The Hadamard transformation is which maps 1, 0 into this 1, 1, and 0, 1 into minus 1, 1. Okay, we were talking of the difference between classical transformations and quantum transformations. That is, the first difference is that the classical transformations are Markovian. So the sum of the probabilities in all states is what is conserved. While unitary transformations, which are quantum transformations, the square of the each column is conserved. So a Hadamard transformation is this transformation that acts basic mixing transformation in a two-state system. But there are two vectors which it maps. 1, 0 maps into 1, 1, and 0, 1 maps into 1, minus 1, 1. So the probability distribution in either case is 1, 1. When you take the square of the amplitudes, it is 1 in each state. If H is applied a second time, then we recover the original state. This has no classical analog. That once you randomize the states, they stay randomized. While this quantum mechanically, somehow it manages to get back to its original state. This is just quantum mechanics at its most mysterious. And to illustrate quantum mechanics, this is the way one illustrates it, that H transformation mixes the two states apparently, and then is able to recover the original state. This is the best and the only way of demonstrating quantum interference. If you have not just one of these H states, but have a number of these H states acting on different bits of the input, then you get something called a Walsh-Hadamard transformation, which is also a mixing transformation since each of those bits is mixed. Mixing in a local sense. But it is mixing transformation. So using these, one designs larger and larger circuits until one comes to something useful. Let's talk about the quantum search algorithm. It needs an inversion about average transformation, which is a unitary operation. And its design is particularly simple. It's the Walsh-Hadamard transformation, and then the selective inversion of the zero state, and then Walsh-Hadamard again. The way to look at this is Walsh-Hadamards are Fourier transforms. I don't know if I mentioned it or not, but that's what they are. So what this is a Walsh-Hadamard, then the DC component is inverted, and then another Walsh-Hadamard. So that's an inversion about average. So what does an inversion about average mean? It is that if you have a setup, setup means a thing with an amplitude in each state, and you know the amplitude vector. The things which have an amplitude equal to the average retain that amplitude after the transformation. And the states that have amplitude above the average become that much below the average as they were initially above the average. So state one is, this is an 8-state system which has prescribed amplitudes in each state. So the amplitude, this is the average, the dotted line is the average of the amplitudes in all the states. So over here, this thing is going to keep these amplitudes the same, which are equal to the average amplitude, and increase the amplitudes of the states which are below the average to above the average. So for example, this thing, amplitude 4, is about this much below the average. This is going to become that much above the average after doing the transformation. Let's see what happens when we do it in a setup with the all equal amplitudes. All equal amplitudes means everything is at the average, so it stays at the average. But suppose you were to reduce the amplitude of one state to -1 by square root of n. The squares of the amplitudes have to add up to 1. So each state has a probability of 1 by n. So the amplitude in each state will be 1 by square root of n. Actually, it will be 1 by square root of n multiplied by some phase factor. But assuming that we were able to make all phase factors the same. So then suppose you were to invert one of the amplitudes. the average, you can show stays approximately the same as 1 by square root of n, because the average is n 1 by square root of n multiplied by n minus 1 by n minus 3 by n. So it only changes by an order of 1 by nth of each amplitude. So it's approximately 1 by square root of n. So if you were to do an inversion about average, these states all retain the same value of the amplitude, while this one, which was below the average, goes that much above the average. It is 1 by square root of n below the average, so it will go 1 by square root of n above the average. So it will become 3 by square root of n. So, and then if you were to do it again, invert it, and then do an inversion about average, it will go to 5 by square root of n, then 7 by square root of n. So in roughly square root of n by 2 operations, it will reach the value so that everything is in this state. Turns out later on it will slow down because the amplitude in these states does not change much in one operation, but in order of square root of n operations, it has clearly moved most of the amplitude into that state. So it'll need a little more than, turns out 0.78 square root of n is the number of operations it needs. That is the best one can do. In fact, it was proven even before I invented this algorithm that it could not be done in order, faster than order square root of n iterations. That was one of the few instances that even before an algorithm was invented, the lower bound had been proved. And calculating the lower bound is much harder than doing the algorithm. So what does all this mean? That we are given an input which takes x bar as inputs and calculates a certain function of x bar, which is 0 or 1. It is 1 everywhere. It is 0 everywhere except in one state, which it is 1. One possible input, it is 1. You have to find the point in which it is 1. The single point which it is 1. You are allowed to hook up some lasers and some log n machinery to this one. How long will it take you to find the single point at which this calculates to 1? Answer is classically, it will be no fewer than n steps. For the same reason, we could search a dictionary in fewer than order n by 2 steps. Quantum mechanically, we need only square root of n queries using the search algorithm. This algorithm generated a lot of other related ideas. And I want to mention one, which is very elegant and is different from the search algorithm, although it uses the same technique. You have an n-vertex graph with one marked state. These vertices can be in any form or pattern. You have to find that marked state. The only operations allowed are queries about whether the particular state is the marked state or no. The state you are is whether is that marked or no. And the only information that I allow given is the local geometry at each place. Whether you are, what states, a particular state you are in connects to. How many queries does it take to find the state T? The answer is order n if the system is quantum, classical, and order square root of n if the system is quantum. This came also as a surprise because it's not obvious how to proceed at all if your structure is not known. I mean, you don't know what kind of graph you are dealing with. So you have to keep getting the same information about the graph and then figure out how to route yourself so as to reach the T state fast. It came as another surprise that it was reducible to square root of n using the quantum search algorithm. This thing found application in photosynthesis. About 10 years ago, some people at Lawrence Livermore observed that photosynthesis this had been known for a while, that the photosynthesis is remarkably efficient in transferring energy to the remote areas of the plant. And in fact, the efficiency of photosynthesis, the bound of how efficient this process could be is about 12%. And it was as high as 10% in many cases. So this, I mean, high efficiency is a puzzle, and it remained a puzzle for a long time until this person in Lawrence Livermore, whose name I forget, discovered that there were oscillations in the transfer of energy. And so they looked at quantum solutions, and indeed this spatial search algorithm seemed directly applicable over there. So the points which generate the power are the states, and the parts that consume the power are the T states. So the question is, how hard is it to transfer the energy from here to here? S is the sunny part, T is the shady part. Similarly, over here is the S states, and here are the T states. Other application of quantum searching is to this amplitude amplification. The quantum search algorithm was if you remember that algorithm, it was first Walsh-Hadamard, then an IT, rotation of the target state, and then in the WI0 bar W. That can be written as WIT, WI0 bar. So alternate operations of W and IT, and then W of I0 bar. If I write it in this form, it turns out that one can get quite a bit of insight writing it in this form. This U is an arbitrary unitary transformation, and just by using the fact that it is unitary, one can derive the fact that what this transformation does is rotate the S vector in this state described by the product of the S vector and U adjoint T vector, so that every time you apply this transformation, it rotates it by UTS or 2 UTS. So in pi by 4 UTS repetitions of this transformation, one gets transformed from the S vector to the U adjoint T vector. If you didn't follow that, just remember that this UIT, U adjoint IS is a very useful transformation to know, which rotates the state vector in this plane. So synthesizing a few words about the practical implementation before we conclude the talk by talking a little more about the about some practical implementations. The reason this quantum computing is hard, or at least seems hard, is because the error correction seems to require formidable machinery. In fact, I've heard it said that quantum computers are basically error correction modules with a little bit of computation piggybacking on the error correction. I mean, the sort of estimates one sees for errors are, I mean, for 1 qubit, which is error correcting, it needs something like 8 to the power of 8 to the power of 8. Something like that. Defective qubits. It takes that. So it can be done in polynomial time, but it takes a huge number of qubits to do that. So the question is, are there devices which are simpler and don't require that much error correction, yet are capable of producing quantum results? Those would be of interest now. These are ideas for implementing quantum computing. No one knows. I mean, these are all ideas which are in active trials. No one knows what the architecture of a quantum computer will be. So it's anyone's guess as to which one will be more popular. This is a discussion of physical implementation of quantum search. Physically, it has been demonstrated and for small systems. And this is called the wave implementation of quantum searching. See, this thing which I told you is applicable wherever you have unitary operations. And pendulum operations are wave kind of structures, which also have unitary transformations. This is well known. And using our pendulum operations, it is possible to redesign these pendulum systems in a way so that very dramatic changes of amplitude take place whenever these things are disturbed in particular ways. So, for example, this was a student at Intel who was doing an internship at Intel, designed this pendulum system, which implemented the quantum search algorithm in the sense that the transformations were of the same nature, but the objects were not superpositions of states. So it's hard to call it quantum, but it demonstrated the same search algorithm. One of the mysteries of natural systems is that they encode their data in the DNA, but the fact that they use bases of 4, 10, and 20 when encoding their DNA in terms of amino acids and proteins. And why this 4, 10, or 20? So Purva Patel noticed that 4, 10, and 20 are the same numbers, which are where quantum searching is most efficient. If you have one query, you can search 4 states perfectly. If you have 2 queries, you can search 10 states perfectly. And if you have 3 queries, you can search 20 states perfectly. So any person who is optimizing his quantum search would choose these parameters. The question is that what nature is doing? This was further backed up by a group in France. They discovered that crack propagation or crack detection is something that can be done by quantum search, and natural phenomena seem to do that. although their analysis was more complex than I could understand. They were using the Dirac equation instead of the Schrodinger equation, which I had used while developing this quantum search. Okay, so to conclude the talk, quantum computing field is in its infancy. The challenges are building a quantum computer, find important applications for it. Factorization and search are the starting point, but hopefully there exist more applications for quantum computers. The hardware challenge is to build a quantum computer that doesn't need that much error correction. If nature can do it, we can do it too. Thank you.
Thank you, Love.